friends, welcome back to another video on quantum mechanics. Video number 27, where we talk about introductory ideas about operators. The operators are very important in quantum mechanics, in particularly while formulating a theory. And then you know that in mathematical techniques very essential while developing the quantum mechanics. We must say that the operator representation is so much effective that it can extract the dynamical information of a system, and which is really contained in the wave function. Basically, we define an operator as the rule, the mathematical rule, by which we connect two different functions or not. And unless it actions some function to give another function, we cannot talk about operator, and as it's a meaningless concept. In quantum mechanics, the dynamical variables become operators, and if you talk about Schrodinger's wave mechanics, where we deal with the Schrodinger differential equation, different kind of differential operators like the Hamiltonian operator, or simply the things that we understand what operator actually mean. While connecting to Heisenberg's matrix mechanics, the operators are found to be matrices which act on the vectors, and the vectors are nothing but wave function in the Schrodinger picture. So in a nutshell, in Schrodinger picture, we find operators as differential operators, and in matrix mechanics developed by Heisenberg, the operators are simply matrices. And in particular, when we talk about operators, the Hermitian operators are the most significant operators in quantum mechanics. We know that there are observations like position, momentum, energy, and the quantum mechanics simply act as Hermitian operators. And we'll find that there will be an equation known as eigenvalue equation, where we find that the Hermitian operators give some definite values, and that's why they're so important in quantum mechanics. Coming back to the definition of operator, we define an operator like this. Suppose we have u and v are two functions. There's always the operator, and you see that the operator O acting on u gives us b. And this O cap, which cap, and simply represents the fact that its operator representation of the variable O. For example, if we take the sin x function, which is acted upon by this dx, we get cos x. So here, ddx is the operator, which acting on sin x gives us cos x. So we see here that there must be two functions for operator to act on, and acting on one function, it gives rise to another function. Usually we use a head or cap and to represent operator, but sometimes we don't use the head or cap while representing an operator. For example, this is the momentum operator, the x component of momentum operator, and this is the operator representation of a momentum operator. And we see here that we don't use cap here on the right hand side, but the symbol for the operator momentum in x direction is kept as like this. But the actual representation of the operator px is not given by something some is cap or head. To familiarize the idea, in this double course, let us list some of the operators which are very frequently observed as dynamical variables in the classical mechanics, which became operators. The energy, total energy, can also be represented as a Hamiltonian operator, which is a function of both position x and momentum. Let us list the other things. Here we see that position is the variable or quantity, and operator representation is x cap, which is simply x. Simply time is t symbol, and the operator representation t cap, which is simply t. And the linear momentum p is represented by minus I suppose the nebula. X component of linear momentum px The operator representation is, we can put it cap here, and this is I minus I suppose del del. It is simply the x component of this p cap. Potential energy Px in one dimension is p cap is equal to Px. Kinetic energy is T equal to P squared by twice m, as we know in classical mechanics. In operator representation, it becomes minus a squared by twice m nebula squared. And the total energy, which can be either energy or Hamiltonian, it can be written like this: E cap equal I cos del del m by T, which we have already encountered in time-dependent Schrodinger equation, or H cap equal to minus a squared by twice m nebula squared plus Bx. This is the kinetic energy part, and this is the potential energy part. And coming back to more operators, these are representations. X component of angular momentum. This is the operator representation. Minus I cos y del del z minus z del del y. Similarly, Ly representation is this. Lz representation is this. We note that in we can represent Lz, the z component of angular momentum in spherical polar coordinate also. This is represented by minus I cos del 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 psi. Here Lx, Ly, Lz, all these three are simply in the Cartesian system, and basically when we deal with spherical system where spherical symmetry is observed, we run into this representation for xz component of angular momentum. And square of angular momentum is minus a square, and the quantity within this square bracket where we have seen theta the polar angle, and then phi the azimuthal angle of spherical coordinate. Thank you, hope you enjoyed it. Don't forget to subscribe to the channel